Okay, now this is two sections, 5.2 and 5.3. Orthogonal sets of vectors, orthogonal projections, which ends up with 5.3, the Gram-Schmidt process. Orthogonal sets of vectors and orthogonal projections. Definition. Let V be an inner product space. Two vectors u and v in the vector space V are said to be orthogonal if the inner product between u and v is 0. Remember this from the dot product in vector calculus. A set of non-zero vectors v1, v2 up to vk in the vector space V is called an orthogonal set of vectors if the inner product between any two vectors vi and vj, where I does not equal to j, like v1 and v2, v3 and v7, in other words, all of them as paired, inner product will be 0. That is, every vector is orthogonal to every other vector in the set. Number 3. A vector v in V is called a unit vector if the magnitude or the norm is 1. Number 4. An orthogonal set of unit vectors is called orthonormal set of vectors. They are just unit vectors, but they are orthogonal, so at the same time we call them orthonormal. They're not just perpendicular to each other, they are all unit vectors. So the vectors v1, v2 up to vk in V is an orthonormal set if and only if they are perpendicular. Secondly, each one of them is a unit vector. Theorem. If the set of vectors v1, v2 up to vk is an orthogonal set of non-zero vectors in an inner product space V, then we call this set of vectors linearly independent. This makes sense because if they are orthogonal to each other, they're not going to be proportional. That's one way to look at it, but of course they're not going to be dependent as a linear combination of a set of other vectors. So the theorem says, in short, if they are orthogonal set of non-zero vectors, like v1 is perpendicular to v2, v1 is perpendicular to v3, and so on, you then have to test for independency. They're going to be linearly independent, which is kind of neat. Example. Verify that these three vectors in R to the 4 is an orthogonal set of vectors in R to the 4, and use it to construct an orthonormal set of vectors in R to the 4. So basically what they are saying, we have three vectors, 1, 2, 3. If they're going to be orthogonal set, 1 has to be perpendicular to 2, 1 has to be perpendicular to 3, and 2 has to be perpendicular to 3, all the possible combinations. And at the end, we're gonna reduce the length of each one of them to a unit vector to call them orthonormal. Verify that, okay, I'm reading the example again. Solution. So I'm gonna call the first one v1, I'm gonna call the second one v2, and I'm gonna call the third one v3. Let's see what we could do. Of course, we're gonna do the inner product in all different ways that we can. So we have inner product of v1 and v2 equals 0. You could verify that. Basically, it's gonna be negative 2 times 0, which is done. The last components will be 0 times negative 6 will be done, and so on and so on. Let's take a look at it. So we have negative 2 times 0, that's a 0. 0 at the end times negative 6 at the end, which is 0. Second component 1 times negative 3, which is negative 3. 3 times 1, which is 3. So it's going to end up adding to 0. Same thing for V2 and V3. Same thing for V1 and V3. So V1, V2, V3 as a set is an orthogonal set. We're gonna, from now on, find the magnitude of each vector, which you know how to do it. We're gonna divide each vector by its magnitude to make it a unit vector. Let's see how we're gonna do that. To construct an orthonormal set, we divide each vector by its norm, or its length. The first vector length is square root of 14. The second vector length is square root of 46. And the third vector length is 2 square root of 6. Now, the orthonormal set will be V1 divided by its magnitude, or its norm. Same thing for V2, same thing for V3. Now, this is called an orthonormal set of vectors. Now we come to a new topic to take advantage of the benefit of orthogonal sets, which means if they are orthogonal, they're going to be independent. We do what's called the Gram-Schmidt, if I'm saying it right, Schmidt process. Let me give you some introduction. Before that, introduction number 1. If you remember the vector sum, the vector sum says if you have V1 and you want to add it to V2, you get the net right here, which is a diagonal inside a parallelogram. So V3 is V1 plus V2. That's called the vector sum. If you want to solve for V2, V2 is going to be V3 minus V1. So now we are looking at vector subtraction. Here's another introduction. If you remember from vector calculus, we had the vector projection and the scalar projection. Today we're going to do a scalar projection, which is looking inside a right triangle. It's going to be the adjacent, and make it a vector by multiplying by the unit vector of the vector that it lays on to make it a vector. So this is called vector projection of B onto A. If you look at the bottom of this page, we have the following. So we have A as being adjacent. Since this is Pythagoras theorem, I'm using ABC now. Cosine theta equals adjacent over hypotenuse, so it's A over C. Cross multiply, you get A equals the hypotenuse C multiplied by cosine theta. So the length of the adjacent as a length, in our case, is going to be a magnitude. It is not a vector for now, is just C cosine theta. Now, in our notes, let me erase this. I was off right here. Okay, let's try again. Now, in our problems not called ABC, we have a vector A and we have a vector B. We're gonna project vector B onto vector A. This here as a length from this idea down here will be the hypotenuse times cosine theta. But because we want it to be a vector, we multiply it by the unit vector of the vector A. Now we have the projection of B onto A, which is magnitude of B cosine theta times A over magnitude of A. Hopefully this was helpful as introduction, because we need it on the process of the Gram-Schmidt process. If V and W are two linearly independent non-collinear, in other words, vectors, then the vector projection of W onto V is being called PWV, as you could see from the notes. So I have two vectors that they are linearly independent, which means they're not proportional, they have an angle between. But what's interesting is we're gonna build two perpendicular vectors instead of just having a different angle, a random angle. Here's a picture of V and W. As mentioned, they're not on the same line. Non-collinear means not on the same line or not proportional. As in my introduction, projecting W onto V and making it a vector is in short called PWV. You could go back to that slide and see how we could rewrite PWV as hypotenuse cosine times the unit vector of V. But let's see it right here. Of course, you could rewind, go back and take a look, but here we go. So the projection P of W onto V is going to be the hypotenuse W, which is a magnitude for us as of the vector W, cosine theta. So in this case, this right here is the scalar projection. That's kind of the hypotenuse multiplied by cosine theta, multiplied by V over the magnitude V, which is a unit vector, makes it a vector marked here in red. See this vector right here? Now that's a length, that's a direction vector, a unit vector, that's a vector projection. Now, focusing on that right triangle, we're going to point to the side opposite to the angle theta. This side right here is going to be my opposite, which I'm going to use the subtraction from my first introduction. It's going to be W minus PWV. Hopefully you could see the arrows, and that should show it to you. That's one reason I had the introduction, because I don't want to explain the subtraction right here. If you need more help, just go back and look at the addition and subtraction from introduction number 1. Thank you. Here's what's interesting. Now this projection of W onto V as a vector is the length of W cosine theta, which is all length, times V over magnitude V, which is a unit vector. That's a vector. This vector is the projection. If you look at this right here, that's the same thing in red. I kept it in red. You could play the game and multiply by V magnitude over V magnitude, which is 1. I mean, this is a legal steps. As long as we multiply by 1 in math and we add 0, we are fine. We're doing this to play the game, as you could see in the following step. So we have V magnitude twice at the bottom side in the denominator, so that's V squared, or V magnitude squared. This V right here is being moved to the right side, and this magnitude V is moved next to the magnitude of W, and cosine theta is pushed a little bit to the right. Look at the numerator. This numerator reminds us of the dot product of W and V. Now you have a new form for the projection of W onto V, which is W dot V over the magnitude of v squared multiplied by v. Now, we have the projection. We have a good picture now right here. We're gonna look at the highlights that I'm showing you. We have a right triangle, and this vector that we just created, after we did the projection right here, we did the subtraction. This subtraction, if you slide it back here and you reposition it at the origin, it's the same color, trying to tell you that these two vectors are identical. So we have v2, as you could see on the left, this vector and this vector are identical. You could graph a vector anywhere as long as it has the same magnitude and the same direction. They're equivalent. That's interesting. So we have now the following. If I zoom in, we started with v, so we call that v1. We had w, we projected w onto v, or v1. We created from subtraction w minus v, and we moved it back to the origin. So that's kind of a neat process. Now we have v1 and v2. If you look at v1 closely and v2, that is perpendicular vectors. So let me read it. So given two linearly independent vectors, v and w, non-collinear, not on the same line, having an angle in between, non-proportional, and so on. In order to obtain an orthogonal set or basis v1 and v2, which we just did, for a two-dimensional subspace of r to the third, we are in r to the third, we do the following. We let v1 equals v. So we're giving v and w, but we're renaming them as v1, v2. We keep the first one as is, and we work on the second one to project, move it up, slide it back to the origin to make another perpendicular, a perpendicular one to the original vector, which we recalled from v, and we call it as v1. So the palm side summarizes what is v1 and what is v2. As you could see, v2 is the subtraction w minus p w v, which is w minus the dot product of w and v over the magnitude of v squared v. Notice that v1 and v2 are orthogonal. So what happened is kind of neat. We had x and y axis, if you want to call it, for now. So we have a vector v1 or v, we had the vector v(w), that they are not proportional. They have an angle in between, which we mentioned. All what we did, we projected this down here with a right angle. We took this right here and we made it a vector projection. We call it PWV. Moved here, that's called the subtraction. This right here, the subtracted one, we replaced it right here, and now we have two vectors. So we had the first one, we kept it as is. After we projected, did the subtraction, moved it back, now we have this one too. This is kind of neat. Those are two perpendicular vectors from the original ones, which were given to me as v and w. Okay, next. In general, let V be an arbitrary inner product space. If we have two linearly independent vectors x1 and x2 in V, we can obtain an orthogonal basis v1, v2 for the subspace of V spanned by x1 and x2 as the following. We call v1 same as the first vector x1. v2 will be the subtraction between the second vector x2 and the projection of x2 over v1. That summarize it in 2 steps. We're gonna have to see it in more steps or more vectors and apply a practice example. In general, let v1, v2 up to vk be an orthogonal set of vectors in an inner product space V. If x belongs to V, then the vector space x minus the projection of x and v1 minus the projection of x and v2 all the way minus the projection of x and vk is orthogonal set to v1 for, I said orthogonal set, it's orthogonal vector x to v1 for each I. This is how you want to do it. I'm not going to read this on the screen. It's going to be time consuming, but you could see the first 2 lines are clear for now. That's what we spent the last probably 7 minutes on it. v3 comes in the same way, but you have to go one more step, and so on. Example on this process. You have x1 and x2 and x3 as provided in R to the 4. We need to obtain an orthogonal basis. Solution. First, we call v1 as x1. We just keep the first one as is. We move x2, we move x3 to make them perpendicular to the first and the second. v2 equals x2 minus the product of x2 and v1 as an inner product over v1 magnitude square times v1, which is x2 is given to me as 1, 1, 1, 1 minus, I'm sure you could test the dot product between x2 and v1, which is 2. The magnitude of v1 being squared is also 2 times v1, which is 1, 0, 1, 0. That simplifies to 0, 1, 0, 1. v3 is x3 minus and also minus again. So you do the dot product between x3 and v1, and you follow it with another subtraction of the dot product between x3 and v2. As stated, I don't want to read the whole thing, but you could follow it and pause the screen to look at more details. This is done completely. It's just basic algebra. The dot product could be done. You could verify that the dot product between x3 and v1 is 1, or simplifies to 1/2 as at the end. v1 magnitude, you could take it and square it and see if that agrees. Now I have v1 and v2 and v3. They mentioned in the problem to make an orthonormal set. So we're gonna find the magnitude of each v1, v2, v3 and divide by their magnitudes to make them orthonormal. So an orthogonal basis for the subspace of R to the 4th spanned by x1, x2, x3 given to me originally is the new ones v1, v2, v3. And an orthonormal basis for the subspace of R to the 4th spanned by x1, x2, x3 is the following. I'm not going to read it. Notice I wrote a comment at the bottom side that to find the unit vector, you divide the vector by its magnitude. So you find the magnitude, which is for v1, 1, 0, 1, 0 will be square root of 2. So divide 1 by square root of 2, 0 by square root of 2, 1 by square root of 2, 0 by square root of 2, and that's what you get. You apply the same method to the other ones, and those are the orthonormal bases. Hopefully I didn't take too long, but it looks like I did. I'm trying not to skip any steps. I'm trying to help as much as I can. So thank you for watching, and I hope that you find this helpful. Trying my best, as you could see, and I will keep improving as we go. I will cover more topics as we go. I'm spending a lot of time for the notes, rewriting, writing, eliminating. I'm not using whiteout. I'm trying to rewrite again, make it clean, to the point, so when I record, it's not something that I have to worry about writing or deleting or using whiteout, whatever you want to call it. So if you like this video, let me know, and thank you for watching.